So without further ado, I'm not going to give a detailed introduction to Dr. Bob Slater because that would take probably the rest of the morning. But I can tell you Bob was formerly the Associate Deputy Minister at the Ministry of Environment here for the federal government in Canada. He's now a professor at the University of Carleton, and Bob talks and teaches about technology and innovation and regulatory science and regulatory process. And probably as someone I've also had the pleasure of working on transformative technology and innovation, such as biotech and a bit of nanotech over the years. So somebody who I couldn't think would be a better moderator for this next session. So Bob, without further ado, if I can ask you to introduce your panel.
Thanks, Bruce. Good morning. And I've reached this wonderful stage in my life when I only do things I find interesting with people I enjoy in a place I like to be in. So that's sort of close to a utopian circumstance. I'm really keen on nano as an example of an innovative technology. And how do you manage it in such a fashion to introduce it into society such that you get the benefits and control any risks that are associated with it? It's sort of, I don't like the man, but Rumsfeld did popularize that notion of, what do you do with what you know? What do you do with what you don't know? And with what you know you don't know? And what do you do with what you don't know you don't know? And nano seems to be a manifestation of that. And with the huge rate of technological innovation, that is the lot of people who worry about these things. I think it's a worthwhile thing to worry about and to try and seize the opportunity as well as manage the risk. There's two favorite institutions of mine well represented in the room. One is Pollution Probe, and the other one is McGill. So that accounts for a lot of the nice people I know, and people like Bruce who are associated with all these things, and Ken and others, and Chris. So that's, and then Montreal is just a terrific city, and I love any excuse to visit. So I hope our guests will, and our presenters will feel the same way. And it's my pleasure to introduce Mark Wiesner. He's a professor in civil engineering at Duke University. He's been appointed a member of the National Academy of Engineering, which is part of the National Academy of Sciences in the US. And this is the highest level of professional recognition accorded to engineers. He works a lot on international cooperation with France in particular in the area of environmental engineering. He's made lots of contributions in membrane technology for water treatment and understanding the environmental behavior and risk of nanomaterials. He's the co-founder and director of the Center for Environmental Impacts of Nanotechnology. And he's going to tell us what he knows.
Okay, well, thanks for the introduction, and thanks to the organizers for the invitation to be here. It's always, on the topic of nice places to be and nice people to be with, it's always nice to be in Montreal. Quebec, McGill is great. My son went here, so I'm a big supporter of this school. So my task this morning has been to very quickly give you some notions about some thoughts I have on opportunities for nanomaterials in the environmental services sector. And so let me just kind of jump to it here. There are some risks potentially with nanomaterials that one needs to evaluate, but those need to be compared with all the other alternatives, and certainly with the benefits associated streaming out of those applications in nanomaterials. The risks, as you'll see, for the materials that have been evaluated to date are, I believe, relatively small. I'm going to go out on a limb there and say that. unless the nanomaterials are made from something that we already knew was dangerous. So if you make a plutonium nanoparticle, you should probably be worried. Also, the applications proposed to date for nanomaterials, while we saw this as a sort of a game-changing possibility some years ago, I think basically what we've seen to date are not really order of magnitude changes in benefit, but are probably more incremental on the order of 10 or 20%. So let me, as a context for this, put up a graph from a paper we did a couple of years ago. We're describing, you could really, this would apply for any emerging technology, the risks and benefits flowing out of that technology, and make the point that the way we perceive or understand or are able to quantify risks and benefits over time, it changes. And the uncertainty associated with those estimates on risk and benefit change over time. So I think in the case of nanomaterials and applied to the environmental sector, nanomaterials in general, we perhaps, I would say, overestimated. In this case here, you see low risk, but we perhaps overestimated the risks associated with nanomaterials. And there's always a lot of hype that goes along with a new technology or group of technologies, and there's, I think, a tendency to overestimate what some of those benefits might be. Over time, though, things sort of settle down, and we hopefully, with enough information and experience, we get to an understanding of whether or not the benefits are greater than the risks, and whether this is a technology that should, in fact, be in the marketplace. The problem is that due to this changing profile of our understanding of benefit and risk, there is, you've probably heard of the valley of death in terms of the development of new technologies. Well, I like to talk about the mountain of uncertainty that exists. There is, due to the uncertainty, one has to overcome that mountain of uncertainty in order to get a technology out on the market. So sometimes you don't want, as I said, those technologies to come out on the market, but other times that uncertainty prevents investors to properly bring their resources to technology developers and move those materials or those technologies out in the market. So the role of doing research on risks is, of course, to protect public health and the environment, and also to really ensure that we have the right technologies in an efficient fashion making their way to market. So as I said, this whole issue of our nanomaterials contaminants in the initial stages, this is often considered as an emerging contaminant. As I said, I think that I'm going to go out on a limb here and say that I don't think that it's primarily it's a drastically dangerous set of materials. If you look at acute toxicities for a whole range of various materials here, and you sort of take the notion that materials with LD50s that are in the range of 50 to 500 are moderately toxic. Most of the nanomaterials that tend to have gotten most of the attention, nanosilver, carbon nanotubes, and so on, they have, in terms of acute toxicity, relatively high LD50s. And so the acute toxicity is probably not something that would be flagged for us, unless, as I said, you're making it from something that we already knew was toxic. Now, what about more chronic effects? You can't probably read all the details here, but it's just sort of to make the point. There's been a lot of studies done looking at everything from impacts on let me just read the list here. Endocrine systems, reproductive systems, and so on. Again, if you really look at what the impacts of those materials are, where they're negative, and there are actually many cases where people have found positive effects on the organisms or the case studied. But where they're negative, they tend to be, first of all, cell culture studies, not whole organism studies. They tend to be materials that we already knew were toxic. And they also, in all these cases, were doing work with the pristine nanomaterials. And so these materials, as they get on the environment, they have a tendency to transform and change. Now, There's beyond sort of the long-term chronic effects, mutagenicity, endocrine disruptor type effects, and so on. There's the ecosystem level effects. And we don't know really what necessarily all the implications are for these effects, but we have observed in work we've done in SAINT, the Center for the Environmental Applications in Nanotechnology, we've observed that there is, in some cases, trophic transfer of materials through food webs. There are effects on things like carbon cycling and nitrogen cycling at levels that we weren't entirely anticipating that we'd see some of those. So again, the significance of that for long-term ecological health and human health is still sort of out. But one has to put this in the context again of what these nanomaterials are and what we're exposed to. I mean, we're sitting in a bath of nanomaterials, and the exposure to engineered nanomaterials is much smaller than the exposure to naturally and incidentally occurring nanomaterials. So sadly, for my research funding, that is where we are. If we'd found these things were to be extremely dangerous, we'd be probably raking in lots of research funding, lots more than we are. Anyway, let me now move on to, very briefly then, some issues associated with applications of nanomaterials. So one that has been brought up is the idea of using nanomaterials as sorbents. I'm not particularly optimistic about it. I think there are some nanobio conjugates that might have some specific applications for being able to remove very targeted contaminants in certain scenarios. The one that's usually cited has to do with removing arsenic from water. And I think this is much more hype, in fact, than actual practical application. Okay, it rests on the idea that if you look at this blue curve here, the adsorption per surface area of arsenic onto nanoiron. This is either magnetite or magamite, so materials that could be removed magnetically from suspension. That if you get down to a small enough size, you drastically increase the amount of material of arsenic that you can sorb onto this nanomaterial. Unfortunately, when you get down to that size, you get past the range where you have superparamagnetic properties of the nanoparticles, where you get the great magnetic separation. So you can't really have both. You can't have the nano effect of the superparamagnetic separation and have the high adsorption rate. In addition, it absorbs so well that you can't really reuse the material. You can't get the arsenic off and then reuse it. So this turns out to be a very, very expensive solution, and there are much cheaper ways to do it. This is a slide that I've used for probably over 13 years that I think is a good application. These are nanomaterials, alamoxanes in this case, but iron or aluminum nanoparticles can be made in this fashion. And it's an alternative to sol gel, where you make a suspension of nanoparticles in a top-down fashion rather than bottom-up, and you can use that to make ceramic membranes. And one of the ceramic membranes that we've made with this is one for proton exchange membranes in fuel cells. I'm not going to touch at all on applications in the energy sector. That's kind of a whole other realm. But just to point out that certainly energy storage and generation is something that's joined at the hip with most of the environmental applications that we're concerned with. One thing you hear a great deal about are photocatalytic membranes. Again, we've done work in this area. Here's an example. I'm not particularly optimistic about this, because when you have to shine light on a membrane in order to make it photocatalytic, well, you have to leave room in the membrane module for the light. And if you look at the cost of membranes as a function of what we call the packing density, the amount of membrane area per volume of module, the costs go up drastically as you go to smaller and smaller packing densities. So you have to leave room for the light. Until we overcome that problem, photocatalytic membranes, I think, are going to be a little bit more hype than actual reality. A recent variety or variation on that theme is the proposal that one do membrane distillation by shining light down onto a membrane that would convert the light into heat and heat the surface of the water, and then you use the temperature difference across the membrane to drive that. The problem with this scenario is that the packing density here is essentially zero, right? Is going to zero, because the volume that you have is essentially the plan area of the membrane all the way up to the sun, right? So taking that area and dividing by that volume gives you essentially a packing density of zero. So it's a very, very expensive solution. There have been a number of proposals for making so fouling is a big problem in membranes, and making membranes that don't foul is something we'd like to get around. One proposal for doing that is putting some zero-valent ions such as silver or bismuth. We've done both in membranes. Again, we've done it, not particularly interesting because these are sacrificial materials. They tend to dissolve and go away with time. A non-sacrificial material that one could put on membranes, perhaps a little bit more interest, it'd be something like any of what I would call in the general sense the fullerene type materials, the caged carbon materials. So fullerenes, single wall carbon nanotubes, graphenes. They do have antibacterial properties, and those antibacterial properties are linked with the electron donor acceptor properties of these materials, not their photocatalytic capabilities. So these things can work in the dark, and you can get some reduction in biofilm growth on those materials. As I said, it's been shown for C60, and we've done it for C60 and carbon nanotubes, and others have shown it for graphene. Another proposal that has been made is to make high flux desalination membranes. So using the properties of carbon nanotubes, if you look at the flux of water through a membrane composed of aligned carbon nanotubes, you get very, very high fluxes. And if the carbon nanotubes are of the right diameter, somewhere around just a little over a nanometer in diameter, then you actually can get salt rejection from those membranes. The problem with that is that we are already, in the current generation of membranes, we're already within a factor of 2 of the thermodynamic limit for separating salt and water. So for a salt separating membrane, it's probably not going to help us much. What happens is you have transport phenomena, these lines forming a V here, represent where mass is moving away from the membrane compared with the horizontal lines, which is the permeate flux. The higher that permeate flux is compared with that V, the more material is going to move to the membrane. So until we come up with different mechanisms for moving materials away from the membrane, we're probably not going to be able to take advantage of a high flux membrane. You might change the mechanical properties of the membrane. So this is work done where you make nanocomposites, in this case carbon nanotubes. People have done this also with some interesting properties using zeolites to improve the flux and rejection of membranes. This works quite well. We've done it, we've scaled it up working with our colleagues in Turkey on this, the Memtech lab there, and we can now spin large volumes of quantities of hollow fiber membranes using this that have attractive properties in terms of less breakage and, as it turns out, rejection as well. And the last example I'll give you here is that of electrically conductive membranes. So one way of doing this is to take carbon nanotubes, and instead of minimizing the amount that you would put in there to get the maximum strength in the membrane, you actually put in an amount that gives you just enough conductivity that you can run a current across that. And that allows you to generate, as it turns out, we wondered about the mechanism for a while, but you end up with the ability to recover the flux at each cycle very, very nicely. And what's happening is you're actually just generating very small amounts of peroxide on the surface of the membrane. So let me just kind of summarize my opinions here in a graph. I've noticed that when you express opinions on a graph, they seem to be more compelling. And so I would say in terms of potential for large-scale application and improvements to the practice, a lot of the things where we're spending a bunch of time or have spent some time, the nanometal, nanofilament membranes, the photocatalytic membranes, and so on, These are probably not going to be the big game changers for us. One thing I haven't talked about, one thing that I think is very interesting, is the idea, another environmental service, of course, is all the waste collection and treatment and recycling. So being able to nano-label the materials that we're using to enable us to identify and sort downstream could be a very interesting proposition. Sensors, a very promising possibility. I think we're going to probably hear, hopefully, Greg Lowry, who's the expert on this topic of nano ZVI and groundwater remediation. Greg, hopefully you'll say something later about that? Maybe? Yeah. Okay. So anyway, there you have it. And with that, I'll come back to my conclusions, and thank you for your attention.